Welcome to Grab and Go Info. CausalImpactpackage created by Google estimates the impact of an intervention on a time series. In this tutorial, we will talk about how to tune the hyperparameters of the time series causal impact model using the R package CausalImpact. Let's get started. In step 1, we will install and import the R libraries. To learn how to use the statistical package R with Google Colab Notebook, please check out my tutorial how to use R with Google Colab Notebook. Firstly, let's install CausalImpact for time series causal analysis. After the installation is completed, we can import the library. To get the code for this tutorial, please check out my blog post on medium.com. I will put the link in the video description. Medium.com is one of the most referenced websites for data scientists. It charges $5 per month for full access. I have been a Medium.com member for many years, and that's the best $5 I spent every month. If you would like to support me to keep providing free content, please use the link in the video description to join the Medium membership at no additional cost. If you prefer not to join, you can still read the post because there are a couple of free monthly posts for everyone to read. Okay, let's continue. In step 2, we will create a synthetic time series dataset for the causal impact analysis. The ground truth of the causal impact is usually not available. The benefit of using a synthetic dataset is that we can validate the accuracy of the model results. The causal impact package requires two types of time series: a response time series that is directly affected by the intervention, and one or more control time series that are not impacted by the intervention. The idea is to build a time series model to predict the counterfactual outcome. In other words, the model will use the control time series to predict what the response time series outcome would have been if there had been no intervention. In this example, we created one response time series variable and two control time series variables. To make the dataset reproducible, a random seed is set at the beginning of the code. Then an autoregressive moving average process is created. For the first control time series variable x1, the autoregressive part has two coefficients 0.95 and 0.04, and the moving average part has two coefficients 0.6 and 0.3. A constant value of 10 is added to the autoregressive moving average process. For the second control time series variable x2, the autoregressive part has two coefficients 0.85 and 0.01, and the moving average part has two coefficients 0.7 and 0.2. A constant value of 20 is added to the autoregressive moving average process. After setting the autoregressive moving average coefficients, 5,000 samples are generated for x1 and x2. The response time series variable y is a function of the control time series variables. It equals 10 times x1 plus 2 times x2, then plus a random value. The intervention happens at the index of 3000, and the true causal impact is 20. A time series usually has a time variable indicating the frequency of the data collected. We created 5,000 dates beginning on January 1, 2000 using the sec.date function. After that, a dataset is created with the control variables x1, x2, the response variable y, and the dates as the index. In step 3, we will set the pre- and the post-intervention periods. We can see that the time series start date is 2001-01, the time series end date is 2013-09-08, and the treatment start date is 2008-03-19. Next, let's visualize the time series data. In the chart, the red line is the first control time series, the green line is the second control time series, and the black line is the response time series. The R causal impact package requires the pre- and the post-intervention periods to be specified. In our dataset, the intervention starts on the 3000 first day, so the pre-intervention time period includes the first 3000 days, and the post-intervention time period includes the last 2000 days. That corresponds to the start date of 2001-01 and end date of 2008-03-18 for the pre-period, and the start date of 2008-03-19 and end date of 2013-09-08 for the post-period. In step 4, we will execute the causal impact analysis on the time series using the default hyperparameters. The causality analysis has two assumptions. Assumption 1, there are one or more control time series that are highly correlated with the response variable, but not impacted by the intervention. Violation of this assumption can result in wrong conclusions about the existence, the direction, or the magnitude of the treatment effect. Assumption 2, the correlation between the control and the response time series is the same for pre- and post-intervention. The synthetic time series data we created satisfy the two assumptions. The R causal impact package has a function called CausalImpact that implements a Bayesian structural time series model on the backend. It has three required inputs. Data takes the dataset name. Pre-period takes the starting and the ending index values for the pre-intervention period. Post-period takes the starting and the ending index values for the post-intervention period. After saving the output object in a variable called ImpactDefault, we can run summary to get the results summary. The summary results tell us that the absolute causal effect is 20, which is the same as the true causal impact. The 95% confidence interval for the absolute causal effect is -10 to 51. To learn more about the causal impact function, please check out my tutorial time series Causal Impact Analysis in R. In Step 5, we will talk about how to tune the hyperparameter niter for causal impact. Niter is the number of 2,000 samples. Bayesian inference usually needs at least 1,000 samples to get reasonable results. The default value for niter in the causal impact package is 1,000, and we changed it to 3,000. The results show the absolute effect of 20 and the confidence interval of -9.8 to 50, which is very similar to the default value. In Step 6, we will talk about how to tune the hyperparameter standardize.data for causal impact. Standardize.data is a Boolean value indicating whether to standardize all the time series before fitting the model. The default value is true. In this example, we set the standardize.data equals false. The results show an absolute effect of 20 and a confidence interval of -11 to 51. It has the same point estimation but a wider confidence interval, indicating that standardizing the data provides better results. In Step 7, we will talk about how to tune the hyperparameter prior.level.sd for causal impact. Prior.level.sd is the prior local level Gaussian standard deviation. The default value for prior.level.sd is 0.01. This default value usually works well for stable time series with low residual volatility after controlling covariates. When there is uncertainty about the stability of the data, the CausalImpactpackage documentation suggests setting prior.level.sd to 0.1 as a safer option. But this option may lead to very wide prediction intervals. We can also not specify a value and set prior.level.sd to null. The summary results for prior.level.sd equals 0.1 tell us that the absolute causal effect is 19, which is slightly lower than the true causal impact of 20. The 95% confidence interval for the absolute causal effect is -131 to 167, which is much wider than the confidence interval from the default values. The larger prior.level.sd produced worse results than the default value, probably because true prior.level.sd is quite different from 0.1. Next, let's set prior.level.sd to null. The results for prior.level.sd equals null show the same causal impact value and confidence interval as the default hyperparameter results. In Step 8, we will talk about how to tune the hyperparameter nseasons for causal impact. Nseasons specifies the seasonal components of the model. The default value is 1, meaning that there is no seasonality in the time series data. Changing the value to a positive integer greater than 1 automatically includes the seasonal component. For example, nseasons equals 7 means that there is weekly seasonality. Currently, the CausalImpactpackage only supports one seasonal component, but we can include multiple seasonal components using the Bayesian structural time series model and pass the fitted model in as bsts.model. In this example, we will set the hyperparameter nseasons equals 7 to include weekly seasonality. The summary results tell us that the absolute causal effect is 21, which is slightly higher than the true causal impact of 20. The 95% confidence interval for the absolute causal effect is -8.4 to 48, which is narrower than the confidence interval from the default values. Since the synthetic dataset does not include seasonality, there is no obvious improvement in the estimation results. But this hyperparameter should give better results for the time series with weekly seasonalities. In Step 9, we will talk about how to tune the hyperparameter season.duration for causal impact. Season.duration specifies the number of data points in each season. The default value for season.duration is 1. For example, nseasons equals 7, season.duration equals 1 means that the time series data has weekly seasonality, and each data point represents 1 day. If we would like to include the monthly seasonality, nseasons needs to be set to 12 and season.duration needs to be set to 30, indicating that every 30 days represent 1 month. In this example, we will use nseasons equals 12, season.duration equals 30 for the hyperparameters. The summary results tell us that the absolute causal effect is 21, which is slightly higher than the true causal impact of 20. The 95% confidence interval for the absolute causal effect is -8.1 to 50, which is narrower than the confidence interval from the default values. Since the synthetic dataset does not include seasonality, there is no obvious improvement in the estimation results. But this hyperparameter should give better results for the time series with monthly seasonalities. In Step 10, we will talk about how to tune the hyperparameter dynamic.regression for causal impact. Dynamic.regression is a Boolean value indicating whether to include time-varying regression coefficients. Since including a time-varying local trend or a time-varying local level often leads to overspecification, this hyperparameter defaults to false. We can manually change the value to true if the data has local trends for certain time periods. The summary results tell us that The absolute causal effect is 20, which is the same as the true causal impact. The 95% confidence interval for the absolute causal effect is -1.6 to 43, which is much narrower than the confidence interval from the default values. The results show that changing the dynamic.regression hyperparameter from false to true improved the model performance. If you have made it this far, you probably find the information in this tutorial helpful. Please click the like button and subscribe to the channel to get notified when I publish new videos like this. To learn more about causal inference, please click the YouTube playlist on the screen now. Thank you for watching and see you in the next video.